And then you see the red button.
Push one more time.
Yeah.
With the talk by Andrew Hardat, who's going to tell us about reverse showers and non-commutative deformation. Andrew?
So yeah, I'd like to thank the organizers for inviting me to speak. This is kind of, it's nice to be at this conference again. It's nice to be able to stay kind of home and go to a conference. So yes, this is, I guess, work in progress with Ludmil. Great, so let's see, what's the idea here? So the basic idea is to sort of look at structures that appear, so you have homological mirrors. So this tells you that the derived category of coherent sheaves on some sort of variety should be the same as, say, the Fukaya-Seidel category of a Landau-Ginzburg model. So the basic idea, at least at first blush here, is to try to sort of see structures on the category of the Landau-Ginzburg model, the Fukaya-Seidel category, and sort of see them in the derived category of the mirror. Okay. So, the basic idea with that is, these are things called perverse Schober's. It's a concept that Kapranovich-Sheckman sort of introduced a couple years ago. So the basic idea is to sort of look for perverse Schober's in derived categories. Okay. So we'll see that, so anytime a category has a semi-orthogonal decomposition and also a Serre functor, you can actually sort of come up with a perverse Schober from this sort of data. And so once you do this in specific situations, we'll sort of see that there's a natural way to produce non-commutative deformations of the original variety of the derived category of coherent sheaves from the data of the perverse Schober and sort of, specific perverse Schobers. And so we'll try to generalize this. So in the case of rational surfaces, this works. So this is okay in rational surface land. But if we try to generalize this, so in the case, say, to something very simple like P3, you'll see that sort of this approach to producing non-commutative deformations that we'll come up with, it doesn't work quite so well. And we'll have to sort of, we'll see that in this case, non-commutative deformations sort of correspond to perverse sheaves of categories on sort of higher dimensional things. Okay. So this is the basic idea. So let's first talk about perverse Schobers. So in order to sort of introduce perverse Schobers, I want to first introduce perverse sheaves. So these are these sort of objects in the bounded derived category of constructible sheaves on a complex space. These are things, so in the derived categories, sort of whose cohomology sheaves sort of behave in a certain way. I don't want to tell you exactly what this is. It's not really useful for the talk. But sort of I want to point out that in many cases these come up, they can be described in terms of combinatorial data. So the basic example that everyone's sort of familiar with is that if you take perverse sheaves on the disk, so that these things are, they come from the derived category of constructible sheaves that are constructible with respect to the stratification, which is just the disk and the point in the center, the point 0. So these perverse sheaves are basically, they come from the following pieces of data. So you take a pair of vector spaces V and W, and you take a pair of maps F from V to W and G from W to V, so one going one way, one going the other. And these are sort of in bijection with pieces of data so that the difference, identity on V, subtract G composed of V, this is an invertible transformation from V to V. Okay. So you can get a bit more deep into this. You can sort of, as Galigo, Granger, and Maisonneuve did, and sort of in a paper which says a lot more than what I'm saying, is that so you can take a skeleton. So this is why I put the board here. So what you can do is you can sort of look at this. You can take so your disk, and you can build what I'm going to call a skeleton of this thing, which is just so this is a disk in C. And I'm going to take the skeleton K, which is just the positive real axis union 0, so the non-negative real axis intersect with this disk. So if you take this thing with this stratification, there's a functor from the category of perverse sheaves on the disk, which are sort of local systems outside of 0, and the category of constructible sheaves on K. And sort of you hit very specific constructible sheaves, and these are things that come equipped with extra bits of data. So these are constructible sheaves that come from basically around this thing. So you have a vector space V sitting over this point, and you have the vector space W sitting over every other point here. And in order for this to be a constructible sheaf, you need a map going this way, and the extra bit of data is the map going this way. Okay. So Kapranov and Sheckman, the idea there was basically that, so the question is, how do you think about constructible sheaves whose coefficients aren't in vector spaces but are in categories? So the idea is roughly that, so if you want to sort of go through the classical definition of a perverse sheaf on a, and sort of instead of having coefficients in vector spaces, you have coefficients in categories, this is a difficult thing to do. But what's less difficult is to define specific constructible sheaves on some sort of easy cell complex like this thing. So the idea is sort of to replace the idea of a perverse sheaf with a constructible sheaf on a simpler space. Okay, so the definition is as follows. So perverse Schober on the disk with respect to the stratification D0 is the data of a pair of pre-triangulated DG categories A and B with a spherical functor from A to B. Okay, so here's what I mean by spherical functor. So a functor of pre-triangulated DG categories is called spherical if this functor has both left and right adjoints and the two following conditions are satisfied. So the functor you get by taking sort of this, this cone here, so F is your functor and R is your right adjoint, you get a natural transformation to the identity functor. And so you can take the cone of this natural transformation and get a functor from your category to itself. So the condition is that this is an autoequivalence. And the second condition is that the natural transformation you get by composing, so this comes from a pair of different things. So this natural transformation is actually an equivalence of functors. Okay, so why should this be sort of a good categorical version of this sort of this definition of perverse sheaves on the disk? So the first thing is that the identity minus GV is invertible. This is analogous to the fact that the cone of FR to the identity, that this is an autoequivalence. And the second condition, well, you'll note that in the case of just perverse sheaves, you just have one map going one way and one map going the other way. So what this says is that, and in the case of, I guess, categories here, I have one map going from A to B and two maps going backwards, the left and right adjoints. So there's not, the second condition here says that these, that the left and right adjoints are sort of related by the twist, by the spherical twist, which is what the functor is called. Okay. So more generally, they give a definition. Am I like crackling here?
Yes.
Yeah. Okay. A lot. Okay. Yeah. I noticed that I crackle when I like move. So maybe I can just use this thing too, because I'm not really moving that much.
You want to use that one?
Okay, sure. I'll just continue and hopefully make less noise. So Kapranov and Sheckman give the definition of a k-coordinatized Schober on the disk with respect to the stratification, which is given by not just a single point, but sort of a bunch of points here. So I'm going to take points in the disk, and I'm going to tell you what a Schober is on this thing. So the k-coordinatization comes from, well, okay, so the Schober part comes from the fact that I'm going to give you categories for each of these points, A1, A2 to AN. And the k-coordinatization is the fact that I'm going to take another base point here, which I'll call Q, and I'll draw non-intersecting paths from Q to each of these points. Let's get rid of that. And I'll draw a path going from Q to the boundary of the disk. This is this union of paths is called K, and this is, I guess, what I'll call the skeleton. Okay, so there's a break group action on the set of k-coordinatized Schobers. So this is essentially the action you get by taking. So say I have these things here, I can sort of move this this path here, and I get a different ordering. Sort of move this path past the path going, I guess this is gamma 1. I can move it past there, and this is my break group action. And so there's an action by this break group on the set of perverse Schobers, which says that I can sort of reorder things, but the price that you have to pay is that sort of you change the functors when you do this. So you change by multiplying by t prime is the inverse of the sphere, t prime I plus 1 is the inverse of the spherical twist of the I plus first spherical functor fi plus 1. Okay, so this, so this is their definition. So what you get out of all this data is a constructible sheaf of categories on this skeleton. So this is essentially the thing you drew before, or I drew before. Okay. So I have to tell you sort of a little bit about what this constructible sheaf of categories is. And so what I do for this thing is I just need to assign, I need to give you a category for each point. I need to give you, for each of these points that I've chosen here, I need to give you a category for each fiber, which will be, I guess, in terms of the definition B, and B here. So the map from, and I need to give you functors from the categories associated to each of these points to each sort of adjoining edge here. So I give you the functor Fn here. I give you the functor, so A1 goes to F1, and so I guess you get the picture. So the only sort of mysterious piece of the data here that I need to give you in order to get a constructible sheaf of categories on this thing is what goes here. And so I won't explain this too much, but this is a category that I'll call Sn, which is essentially going to be some sort of category of representations of the AN quiver with coefficients in the category B. Okay, I'll just bang my chest.
I'll switch it up.
Okay, sure. So I'll just keep talking as that happens because I'm not sure how my time's going to be. Okay, so in the future, what I'll do is I'll use a different skeleton. I'll use something that looks more like this, but sort of encodes the same types of data. Thank you. I don't know. Okay, so what I'll do is I'll take the skeleton that doesn't sort of go from some base point here, is I'll sort of ignore the base point, and I'll just draw points. So I have a sequence of categories, and I'll use that sequence to build something like this. So, I mean, maybe I don't need to draw it because it's already on the board, but yeah. So this is sort of what I'm doing.
I think you muted it when you put it on.
Oh, I muted it? That's great. Okay.
The green or
Which button here? Which button is the
top,
one?
on the top.
Top one? Okay. Oh, great. Okay, there we go. Okay, so in this case, the categories that I'm going to assign to each point is the category that I'll call square brackets AI comma B, with Fi sort of kept there. So this is a category whose objects are pairs of elements, A and AI and B and B, and they're going to be connected by some map mu. So this is a closed degree zero morphism in the category C. So C a, is this what I'm saying? It's going this way. FAB, sorry. From FA to B. Okay, so it's a closed degree zero morphism in there. So this is what happens at the points that are not P5, and at the point P4, I'm just going to put the category. Oh, sorry, this shouldn't say. Oh yeah, so yeah, okay. So my last line says what I want to say about P5 is that I put the category A5. Okay. So I guess it's just an example. Okay, so the point is that anytime you get a perverse Schoberg, this is sort of the same thing as saying you're giving me a semi-orthogonal decomposition. Well, these are very closely related ideas. So I'll give you the definition of a semi-orthogonal decomposition. And so I wrote it this way because I had trouble getting LaTeX to actually give me the triangles. But the idea is that you get a bunch of categories, a bunch of full and faithful, full subcategories of A, so that every object in your category has a decomposition or can be written in sort of this way. So I have A2 here, I have A1 here, then I go to some B1, I get a triangle here, B2, I get a triangle here, A3, and on until I get to Bn minus 1, then I get Bn, and sorry, this is this, then I get an An here, okay? And this Bn is equal to A. So every element of my category can be decomposed in terms of a triangle like this, where AIs are living in the categories big AI. Okay? And furthermore, these things there's no sort of morphisms going backwards in this decomposition. Okay, so, and I haven't explained exactly what this means, but if you take the category of global sections of any perverse Schober, by which I mean you take this constructible sheaf of categories that I built on the skeleton, then this category will always have a semi-orthogonal decomposition. So furthermore, what you can do is that if you have a category with a specific type of spherical functor to the category C, and this category A has a semi-orthogonal decomposition, you can build sort of more spherical functors from this. Okay? So what does this say? So if you have a spherical functor from A to C, so that the cotwist of this spherical functor is actually the Serre functor up to shift on the category C. And if A admits a semi-orthogonal decomposition into subcategories, so I'll just denote the embedding functor by Ji going from AI to A, then the composition of these two functors, this thing is spherical, and this again has a cotwist, which is the Serre functor on AI up to shift. Okay, so I can build a perverse Schober from this data pretty easily. And of course, I can do something like take this the perverse Schober that I get by just putting the category A here and the category C here, and then connecting them with the functor F. But what this theorem says is that if A has a semi-orthogonal decomposition, I can do even more. I can take the perverse Schober that I get by putting the category AN here, and I'll draw it in sort of the Kranov-Shechtman way. AN minus 1 here, dot, 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 to A1. And I can get a perverse Schober that looks like this, where C is the category over each edge here. Okay? S and C. Okay? So what this theorem tells you is that you can basically, semi-orthogonal decompositions allow you to sort of take up a simple perverse Schober and break it up into a more complicated one. Yeah, so this is what I just said. So the example, I mean, the basic example that I like is that if you have say a smooth variety X, and you have some smooth anticanonical hypersurface section of this variety, so then there's an embedding functor from Y into X, and then there's a pullback on the derived categories of coherent sheaves. So this functor is spherical, and this sort of satisfies the condition that I wrote down in the previous theorem. So specifically, if X is Fano, there's usually going to be an anticanonical section, a smooth anticanonical section, and there's also going to be some sort of semi-orthogonal decomposition. So this sort of structure does show up in nature. So furthermore, Ed Segal proved that if you have any audio equivalence of a category can be basically reconstructed as a spherical functor, or as the twist of a spherical functor. So what this means is that you can always build such a pair. So if I have a Serre functor, so given the conditions in this theorem here, this is a spherical functor. So given a category with a Serre functor, I can always build such a thing. Okay. So what can you do with this? Well, you can say that basically any time you have so the idea is that if I write down this perverse Schober here, okay, I'm walking around. So let's just state this theorem, and then I'll talk a little bit more about this. So the theorem is that if you have any pre-triangulated DG category with a semi-orthogonal decomposition and a spherical functor like this from A to C, whose cotwist is the Serre functor on A, then if you take the category of global sections of this perverse Schober, this constructible sheaf of categories that I've built from the perverse Schober, then this recovers the category A. So this is my claim here. So the bit before this, the bit about Segal's theorem, is to say that any time I have a semi-orthogonal decomposition on a derived on a category, and that category has a Serre functor, I can build such a thing. so what this says that if I have so anytime that you have a semi-orthogonal decomposition on a category with the Serre functor, this thing is the category of global sections of some perverse Schober. And so what do I mean by category of global sections? So I'll just say a little bit about this right now. Is that, so if I have this data, what I'm doing actually is I'm sort of giving you functors from a bunch of categories to another set of categories. And so this builds a diagram in the category of DG categories. And what I want to do is I want to take a homotopy limit over this, this diagram of categories. So that's what I mean when I say global sections of a sheaf of categories. Okay, so let's look at an example, a really basic example. So this example is of P2. So if you have P2 and you take a smooth elliptic curve living in P2, then the functor from dB co of P2 to dB co of this elliptic curve, this is spherical with co-twist the Serre functor up to shift. Then you can take the Beilinson exceptional collection on P2, and this gives rise to a bunch of to a semi-orthogonal decomposition of P2 first of all. And therefore, you get a bunch of spherical functors from dBk. This is just the derived category of complexes, K complexes, to the derived category of coherent sheaves of E, of this elliptic curve. So what this means is that we can reconstruct the category, the derived category of coherent sheaves on P2 from F1, F2, and F3, these three spherical functors. Okay, so now I said I would sort of talk about how we can sort of get non-commutative deformations of derived categories from this expression in terms of perverse Schobers, and sort of this is my explanation of this. So if you have a spherical object on an elliptic curve, this thing can actually admit deformations. I mean, the dimension of x1 is equal to 1. So therefore, we can actually deform the functors fi that I wrote down here, f1, f2, and f3, by composing with automorphisms, essentially, of the elliptic curve. So take something in Pix0 of the elliptic curve. This gives you an automorphism. And what you get is you get a deformation of the perverse Schober. And when you take global sections of this perverse Schober, what you get is some new category if you do this deformation of the spherical functors. So formally, to bring this sort of in line with classical, but sort of well-known stuff on deformations of P2s, on quantum P2s, what you do is the following. So you take an elliptic curve, a smooth cubic curve, take L to be a degree 3 amplifying bundle on E, and take tau to be an automorphism of E, something in Pix0. So then you can build a perverse Schober given by the spherical functors. So in this case, what I'll do is, so you take something like this, just the 3-prong thing. So I put the derived category of the elliptic curve here on each fiber here. I put the category dBk here. And sort of I'm deforming these things by sort of essentially twisting the functors fi that I'd written in the previous slide by an automorphism of E. Okay, and if I do this in a specific way, I take O, L, and so say I'll put O here, L here, and tau, go back L squared here. This gives me something classical. So if you know things about quantum P2s, this is exactly, I think, this is sort of an old construction of non-commutative deformations of P2s. This is the data involved in this. And so this gives us the derived category of coherent sheaves on what's known as non-commutative P2. So this is very close to a construction that was given by Bandal and Polishchuk. And what they did is they talked about this in terms of things they called elliptic exceptional collections, which is sort of the same thing. These are spherical objects on the elliptic curve. And they showed that sort of, essentially what they showed is that this construction, taking global sections of this perverse Schober, certainly not in this language, but they showed this, recovers for you all non-commutative deformations of P2. And so the same approach can be taken for any rational surface with a smooth anticanonical section. And this will sort of produce for you non-commutative deformations. Okay, so what you can try is that you can say, okay, I have this sort of thing that can sort of sometimes build for me non-commutative deformations. What happens if I try to do this on higher dimensional varieties? What if I say take non-commutative, take a P3 and try to build non-commutative deformations of this thing? And so this doesn't really work. So if you take higher dimensional varieties, say K3 or a Claviau threefold sitting inside P3 or P4. You take these spherical objects; they don't have deformations. We can't sort of pull back along some sort of deformation of this variety. So what we have to do is basically this. So instead of taking instead of keeping the fiber category, this category DDE fixed, what you do is you take the you deform that category in a non-commutative way so that the spherical functors are preserved. So this is what we're going to try to do. So if you do this, then what we'll get is we'll get categories whose global sections turn out to be non-commutative deformations of P3.
All right, thanks a lot.
Okay. Yeah. So we can't do this with smooth anticanonical sections. So there's a theorem of Kanazawa, or some work of Kanazawa, which basically shows that when you deform P3s non-commutatively, usually these things don't have smooth anticanonical sections. So what we need to do is we need to take degenerate anticanonical sections. So there's also work by Polshchuk which suggests this. So specifically what he does is he looks at Poisson structures on P3, and he shows that if this Poisson structure has a Poisson divisor, then this Poisson divisor has to be the union of a pair of quadrics meeting transversely, or the union of a hyperplane and a cubic. So what we're going to do is we're going to take hyperplanes and unions of pairs of quadrics meeting transversely, or unions of a hyperplane and a cubic, and we're going to sort of try this with that. Okay?
What will happen if you don't have an anticanonical divisor at all?
Yeah, I don't know how to produce non-commutative deformations.
Then we cannot.
Yeah, exactly. So the point is that all the deformations that I can produce this way, they come from non-commutative P3s with non-commutative anticanonical divisors. Yeah. Okay. So if you take the natural functor from the derived category of coherent sheaves on P3 to the category of perfect complexes on Q1 union Q2. So this is again spherical and has co-twist equal to the Serre functor on P3 up to twist. So the theorem that I gave a couple slides back that says you can reconstruct the derived category of P3 from a bunch of exceptional objects or a bunch of spherical functors to the category of perfect complexes on Q1 union Q2, this still holds. So I can still build a perverse Schober. In this case, it'll have a bunch more things, and the generic fiber will be perf Q1 union Q2, and then I'll have a bunch of spherical functors sitting here. I can still build such a thing that'll recover the derived category of coherent sheaves on P3. So the approach is going to be to build okay, so what I'm going to do is I'm going to try to build non-commutative deformations of Q1 union Q2 using sort of the same approach I used to build non-commutative deformations of P2. Okay, so I mean the idea is that the following. So smooth quadric hypersurfaces in P3 are just P1 cross P1. So they emit this sort of semi-orthogonal decomposition. So I'm using notation for bundles on P1 cross P1, but this is it. So these bundles give again spherical functors from the derived category of K complexes to the derived category of coherent sheaves on E. So this is just sort of giving a more abstract description of what you get on the elliptic curve. I apologize for the typo. So the image of the object K in DB co E is either O of E, a degree 2 line bundle L1, L2, and L1 tensor L2. Okay. This is just the restrictions of O1, 0, and O0, 1 to the elliptic curve and the tensor. Okay, so now we have another perverse Schober, this time living over I guess I'll draw it in the way I've drawn it before. So I'm using several different pieces of sort of ways to draw these things, but they're all sort of equivalent. So I get a perverse Schober over this thing so that I have something like O here, L here, or L1 here, L2 here, and L1 tensor to L2 here. Okay, and over this thing I have dv co of E. So my point is that each quadric can be recovered as the category of global sections over subject. Okay. And you can build the derived category or the category of perfect complexes, this thing, as a fiber product of these two things. So for each quadric, I have such a thing. The elliptic curves agree because they intersect in the same elliptic curve. So I can take the fiber product of these things, and the fiber product just turns out to be sort of gluing these two complexes together and then taking the category of global sections on this total. Okay, so spherical objects on this fiber product, this thing is now a fiber product of two different things. So what I want to say is that there are spherical objects on this Q1 union Q2, which can be built from exceptional objects on Q1 and Q2 separately. Okay, so this is sort of in the same vein as the following result. So if you have an exceptional object on a category A, and you have a spherical functor from A to B, so that the co-twist of this functor is the Schrödinger functor, then the image of this exceptional objects in B is a spherical object on B. Okay. So this is something that goes back essentially to Seidel and Thomas. So what you can do is you can say, okay, so assume now I have two things, both of which have an exceptional object, like in this case. So in this case, I'll get an exceptional object from some sort of thing going here and something going here. And so if they agree, when I glue these two complexes together, what I'll get is a spherical object on the total candy. Okay, and so this is the content of this theorem. So if you have two different spherical functors, so that the co-twists are S1 and S2 up to the same shift, and if you take E1 and E2 to be exceptional objects on A1 and A2 respectively, so that when you map them to this sort of the category in the middle, B, then E1 and E2, then there's sort of an induced spherical object on the homotopy fiber product of these categories. Okay, so I mean, a simple case in which this holds is that if you have an exceptional object on a category A, then you can sort of glue this to give you a spherical object on the sort of the self-homotopy fiber product. Okay. So what we want to do now is we want to build non-commutative deformations of each side here, take the homotopy fiber product, build spherical objects in this homotopy fiber product, and then build a perverse Schober that recovers non-commutative P3s. This is the goal now. Okay, so we can do this in much the same way that we did sort of build non-commutative deformations of P2. Yeah, okay, ignore that. So what we do is we take two, just to sort of here, we take two line bundles here, L1 and L2, and we'll take the same elliptic curve and the same L1 and L2 here, and L1 tensor to L2. Guessing you probably can't see this very well. But so what I'm going to do is I'm going to take an automorphism of the elliptic curve, and then I'm going to pull these spherical objects back along this automorphism and pull this back along this automorphism. So what I'm doing is I'm building this way, sort of in the same way I did for P2, a non-commutative deformation of P1 across P1, or Q. So this gives dB co, which is something I'll call Q mu. And I have another copy of dB co Q mu. And I'll glue these things together to get a non-commutative union of quadrics. Okay, so this is sort of what I'm saying. Right, we sort of do the same process, take the homotopy fiber product. Yeah, any questions so far? Like, how does this go? Okay, just wanted to check. Okay, so how do we build sort of spherical objects on the category of perfect complexes? Or sort of, how did we, knowing what we know now, that the category of perfect complexes on Q1 union Q2 is a fiber product of sort of two different categories, and knowing that we can build spherical objects on this fiber product using exceptional objects on each thing on each side, how do we build this perverse Schober? Like, how does this whole thing work is my question. And so what does this mean? Well, what are these spherical objects here? So this is O, something sort of induced by O, the restriction of O1 to Q, or so, well, O to Q. The second thing is O1 restricted to Q, and O2 restricted to Q. And the third thing is O3 restricted to Q. Okay, so this is the Belinson exceptional collection on P3. So these are the things restricted to Q that give me the spherical objects from which I can reconstruct P3. Okay, so what does this give you? On each Q1, this is O on Q. This is a thing on the on this. Okay, let's see. Okay, so let's see. This is an exceptional object on OQ1. So these things glue together to give me O restricted to Q. Oh, sorry, this is Q1 UQ2. Hopefully this is understandable. So what I'm doing is I'm taking now O11 on Q1, gluing this to OQ2, 1, 1, and then I keep doing this. So these gluings together give me the spherical objects that I'm looking for to reconstruct P3. Okay. So I have Q1, 2, 2, glue this to OQ2, 2, 2, O1, 3, 3. Glue this to O Q2, 3, 3. Okay? So it's the gluing of these exceptional objects which give me the spherical objects here. Okay, so how do these things deform when I deform Q1 union Q2 is the thing that I'm asking. Okay? So what I'm going to do is I'm going to take, well, I get exceptional objects on these non-commutative, this non-commutative Q1 and non-commutative Q2, which are sort of the same thing. I get exceptional objects coming from these guys here. Okay, so I get an exceptional object coming from L, L2, L1, O, and tau, pull back, L1 tensor to L2. Okay, so I get exceptional objects here. So what I'm going to do is I'm going to take, so this thing basically comes from taking this and gluing it to this thing. So the object here. So the exceptional objects corresponding to these vertices in the two different sides correspond to this, this one here. And this, gluing these together, this gives you a spherical object on the category of global sections of this Schober. This corresponds to this thing here. And these guys, these correspond to taking the Serre functor on the category of global sections of this thing and applying it to this. So this is equal to S of this thing. Serre functor applied to this, and the Serre functor applied to that. Okay, so my point is that when I take non-commutative deformations of Q1 union Q2, there are natural objects which correspond to deformations of the spherical objects on Q1 union Q2, which give you this perverse Schober. Okay. All right. So the upshot of all of this is that, so for any non-commutative deformation C of the quadric, sorry, I shouldn't say, of the quadric hypersurface, we can glue this quadric hypersurface to itself, and we can pick out exceptional objects on both copies of this quadric hypersurfaces. And these exceptional objects, once you build spherical objects, once you build spherical functors and put this together into a perverse Schober, this will give you a non-commutative P3. Okay, this is what this is sort of the construction. Okay. So therefore, we can actually deform a perverse Schober to get non-commutative deformations of P3. So just as I was saying before, I mean, in the case of P2, what we did was we sort of deformed the perverse Schober by keeping the fiber category constant and deforming the spherical functors. But this didn't work in this case. Okay. So one thing that I want to point out is now, what have I done? What have I really done here? Okay, so I have two different pictures. So this sort of describes the fiber category, and this, in a sense, describes the base. I'm sort of mixing my two pictures. So I have a one-dimensional complex, which essentially fibers over a one-dimensional complex. So the question is there some sort of two-dimensional complex here that encodes the same data? Okay. So can I build a two-dimensional complex which supports a sheaf of categories, a constructible sheaf of categories, whose category of global sections recovers the derived category of P3 and non-commutative P3s. Okay, and so this is what I want to say is true. So we can always encode spherical objects or spherical functors in such a category, in a category like this, or we can often do this using the category of global sections of a two-dimensional complex. So this is the complex that I want to talk about. So it's something that looks like this. So what I'm doing is I'm bringing these two things together, these ones here together, to a single point. Okay. And so I can build a sheaf of categories on this thing, so that the category of global sections on this whole thing gives me, oh, in this case it's not so interesting, it's just the derived category of complexes over K. So this is a description of exactly what the sheaf is. But what's more interesting about this is that when I build this category of the sheaf of categories over this thing, it doesn't just encode that, it also encodes the spherical functor, which is the embedding of the category I get by going, say, O to O here. It encodes the embedding of this into the homotopy fiber product. Right. Okay. So this whole construction basically depends on the fact that we're basically bringing two things together, and these two things represent essentially the same object in the category between them. Okay, so what this will do for us? What will this do for us? Sort of, given the expression we have right now, is this is a two-dimensional complex which will encode the embedding of the object, this object here, into this category. So in order to sort of build a two-dimensional complex that'll encode the embedding of these other spherical objects here into this category, what I need to do is I need to understand how mutation works in terms of perverse Schobers. Okay? Okay. So what I want to do is I want to give you a two-dimensional complex. So what do I mean? So anytime you have a semi-orthogonal decomposition, you can sort of reorder the components in this semi-orthogonal decomposition. But the cost of doing this is sort of changing the way you glue everything back together. So this is called mutation. So what you can do is you can encode mutation in terms of a two-dimensional complex. So what do I mean by this? So if I have two different semi-orthogonal decompositions of the category, these will give me two different perverse Schobers whose categories of global sections give me the same category. Okay. So I want to relate these two different perverse Schobers. And so here's the theorem that sort of tells you how to do this, or how this sort of works, is that if you take, basically, if you take a bunch of spherical functors, then the category of global sections you get on the corresponding perverse Schober is that is sort of the same category as the category of global sections you get on a different perverse Schober. And this is the category of, this new perverse Schober is the one that you get by sort of leaving everything constant, except for maybe these two things, where you switch the two. And that this is the same as the thing you get by changing, keeping the categories constant, changing the order, and switching the functors. So that f of j plus 1 is equal to f of j, so that doesn't change. But f tilde of j is equal to tj plus 1 times f of j plus 1. So this is essentially the same as, I can't go back, but Kapranov and Shekman have this equivalence between different perverse Schobers. So what this theorem is saying is that Kapranov and Shekman, if you take the global sections of the categories of global sections associated to equivalent perverse Schobers, you get equivalent categories. Okay, so this can be encoded by a two-dimensional cell complex and with a constructible sheaf of categories. And you can build something very simple like this. This is probably not quite the right thing to use. So the fact, whether it's whether I'm moving this like this or this like this is encoded by the constructible sheaf of categories that I'm not going to tell you how to build on this two-dimensional complex.
Wait, can you explain that picture? Why is it two-dimensional? What are the two cells?
Oh, yeah, the two cells are the things going between the lines. So this is like...
Well, all four of those empty places are two cells?
Yes. All four and off to the sides as well. So what we can do, what can we do? Well, we can, okay, so what we do is we want to take this category here. And so maybe I'll give a better drawing of this with my eraser go. Okay, well, anyway. What do I want to do? I want to start with the original sheaf of categories here, encoding Q1 union Q2, or its non-commutative analogs. And I take this thing here. And so I want to go along like this. So for the object O that I get by gluing O of Q, by gluing O of Q1 to O of Q2, what I can do is I can just do this. I can just do this here. This is what I was saying before. I get this, and everything's fine. I build a sheaf on this thing, and this encodes the embedding of this spherical object into the category of perf Q1 union Q2. For the second spherical object, what I have to do is I have to mutate a bit in order to do the right thing. So I take something like this. And then what I'll do is something sort of like this. I'll mutate. And maybe I only have to mutate once. I'm not sure. I can't remember. Then I'll bring things together like this. I'll do the same thing on the bottom. Get something like this, a two-dimensional complex like that. And this complex, something like this complex, will encode the embedding of O of Q of O of 1, sorry, this one here, of Q1, 1, and Q2, 1, 1, into the category here. And so once I have complexes like this that I get by mutating, by sort of changing order, and sort of pinching together at the ends, these things that sort of correspond to these spherical objects on the fiber product, I can glue these things together at their edges like this, at the edges, at sort of the edges here. So maybe this drawing's not so great. Maybe what I should have been drawing is something like this, is something going off into the board here. So I do something like this. Okay, so these are sort of two complexes. Each supports a perverse sheaf, perverse sheaf of categories, constructible sheaf of categories. Then I build another thing off here that after mutation encodes, say, this object, and another one that encodes this object. And I build something going off to infinity, maybe. So I have some other mutation here. So you can sort of fill in the gaps. It's kind of complicated after that point. So that essentially from this, what you get is you get a two-dimensional complex equipped with a constructible sheaf of categories, whose category of global sections is P3. And if you deform, sort of in the way that we described before, everything on the fibers here, everything else comes along for the ride, and you get a sheaf of complexes, which encodes non-commutative deformations of P3.
In what direction am I supposed to read this diagram? I mean, is there some sort of way to read it as forward to back, like you're doing something?
Oh yeah, sorry. So the original objects sit here. So say I have something like 0, 0, 0, 1, 1, 0, 2, 2. Oh, I forgot 0, 2, 2, and 0, 3, 3, and symmetrically going down as well. Okay. So these things stay the same along here, and so as I go here, I mutate my exceptional collection so that if I look at the category here, this is the same category if I take the global sections along this slice, but I mean these functors are different. So the categories here are the same, but the functors are going to be different.
What's happening in that bit you've drawn at the back?
Oh, this is sort of yeah. Okay, so you should think about this diagram as being fibered over this diagram. Right, so this is like my thing going off to infinity. I draw this in a circle. I have points here. I have this thing going off to infinity to the boundary of the disk, and I have these things stopping here. So this should correspond to, say, this point here. This thing should correspond to this point here, and this one corresponds to this. So is it
Thanks,
clear?
yeah.
Yeah. Okay. Good. So this is some sort of two-dimensional complex fibered in one-dimensional complexes over a one-dimensional complex. And the category of global sections that you get on this entire thing gives you the derived category of P3 and its non-commutative deformations. Oh, ooh. Okay. Great. Okay. Okay. So I just want to explain very briefly why I did all this. I mean, it's kind of nice. It's interesting. Like along the way, there's sort of interesting things that come up, but it's you know, it's a bit convoluted just to get non-commutative deformations of P3. So the reason is that this sort of data, the braiding data that I use to build this. So in order to build this, what do? I have a bit of braiding data that comes from mutations, and I have collision data right at the end. Okay, so that's the data involved here. So what I want to claim is that if you look at the Landau-Ginzburg model of P3, the same braiding and collision data appears very naturally. Okay, so very vaguely, the Landau-Ginzburg model of P3 is C star cubed equipped with this function. So each monomial in this expression will correspond to a toric boundary divisor in P3. So what I did to sort of build this was I took two quadrics in P3. So what I want to do very heuristically is split this up into two pieces, each corresponding to a single quadric. Right, okay. So what I get is instead of just one function on C star cubed, I get two different functions, which I'll call f1 of xyz and f2 of xyz, written this way. So this gives me a map from C star cubed to C squared, whose fibers are then punctured elliptic curves. So you can sort of put this back together to give yourself the the f that we started with by composing f1 and f2 with the map g from c squared to c, which sends t1 and t2 to t1 plus t2. So you can compactify c3 relatively to this map to c squared and get an elliptic fibration over c squared. And this fibration is then degenerate along the curve t1, t2, this thing I've written here. Okay. So at the points, this is just a description of how this elliptic fibration looks. And so maybe I'll just jump to the end a little bit and sort of describe. No, maybe I won't. Okay, so along these loci, you have a degeneration of your elliptic fibration. At the points t1 and t2 equals 0, where or t1 equals 0, t2 not equal to 0, and t2 equals 0, t1 not equal to 0. you get a chain of 2 rational curves. At the center, you get a chain of 4 rational curves in a circle, sort of arranged in a circle. And everywhere else at the loci, the locus t1 squared, t2 squared minus 16 equals 0, you just get a nodal elliptic curve. So you get a map. G gives you a map from this curve delta to C, and this is going to be ramified over the point 0 and the 4th roots of unity multiplied by some constant. And the topology of this curve, or this pair C delta, is determined by certain braid actions along the fibers of delta under the map G to C. Okay. So what you do is you take a base point somewhere along C so that the fibers above this thing in the curve delta are precisely 6 points. And then you draw little curves, or draw paths from this point Q, I guess, to the point 0, P0, P1, P2, and P3, and P4. Oh, sorry. P0 to P3, where the map G restricted to delta ramifies. Okay, so if you sort of trace what's happening to these points, the one way you can represent this is that these points, they sort of braid around each other. And eventually, since these, if you look at it, the ramification points of this map are simple, what's going to happen is these things are going to braid around each other, and then 2 are going to come together. Okay, and a pair of PIs collide. So understanding this braiding, the way these things braid around each other and which ones collide at the singular points, the topology, basically this determines exactly the topology of the pair C squared at delta. So this is a bit complicated, and it's not so, well, it's complicated, but essentially up to some sort of small issue. So the issue is that, in this case, I start with 8 points, and in that case, I have it's just 6 points. But what you should think about is the fact that maybe these 2 points come together. So just push all these 2 things together, push these 2 things together to one single point, and after you do that, the braiding data you get by looking at this curve, this pair of C squared delta, is exactly the same braiding data you get from this reconstruction of the derived category P3. Okay, so the explanation I give in very vague terms and sort of perhaps is a bit not so great is that basically this map F1, F2 will give you a perverse sheaf of Fukaya categories over C squared. So this is going to be a local system outside of the degenerate curve delta. So one can build sort of a combinatorial skeleton for the pair C delta out of this braiding data. And so the restriction of this perverse sheaf of Fukaya categories, whatever this is, this restricts to the skeleton I built out of the combinatorial, this sort of braiding data. And this gives you a constructible sheaf of categories on this skeleton. And so when the idea, I guess, is that what's happening is when I'm taking this perverse sheaf of categories of the skeleton should correspond to what I've drawn here, coming from just the categories. And the perverse sheaf of Fukaya categories, or the constructible sheaf of Fukaya categories that you get by restricting to this thing, should correspond to the constructible sheaf of categories I wrote down here. And so when I take global sections of this constructible sheaf of categories, I should be getting the Fukaya-Sadel category of the fibration. So the fact that so when I build this map in sort of the topological case here with C delta, what I'm using implicitly is the map F from C squared to C to build this skeleton. So this is sort of some possible explanation of why there should be a relation between the skeleton I get combinatorially and the Fukaya-Sadel category. Okay, and that's all I have to say.
More questions?
So you were constructing these non-commutative deformations by changing the gluing map somehow in the sugars?
Yeah.
What does that correspond to in the Fukaya-Sadel category?
So in this Roux, Katsurkov-Orlov paper, so they get non-commutative deformations of Del Petzos. Or I guess it's sort of the same thing, essentially. It should correspond to changing like a symplectic structure. Yeah.
But the gluing indeed is different, so the spherical function changes around this single point. Yes, Phil?
Is there, I mean, this is just a notational question, is there a special name for the spherical functors whose clocus is ser? They seem to have a distinguished role in the story.
Yeah, I think they've been called like it's a Calabi-Yau pair, I think is the name I've heard. Yeah.
No, so I heard about this work by Brent Kim where he classified the non-commutative P3s, and there are 6 irreducible components, and they have to do with the corresponding foliation in the Poisson structure. Is that geometry connected with?
Yeah. So two of the non-commutative deformations that he constructs are so there's one that's a Skleana algebra, I think dimension 4, and then there's the other that's a central extension of the dimension 3 Skleana algebra. These are the two that I get from taking the different decompositions of the anticanonical into a pair of quadrics and a cubic intersect a hyperplane. So the cubic intersect a hyperplane gives you the central extension of the 3-dimensional Skleana, and this one gives you the 4-dimensional Skleana, the one that I described. Yeah, so there's a close relationship. But these are, he mentions the work of Bolshchuk in there in describing the Poisson structures that he sort of quantizes.
And the other ones are not?
Yeah, so I'm pretty sure the other non-commutative deformations he describes don't come with anticanonical divisors, so they won't show up in this sort of construction, unless you have more ideas with them.
Other questions? Well, if not, let's thank Andrew again. So last call, if you go to dinner, please see the secretaries behind there.